Welcome back. We are discussing a new chapter today. We are on to section 3.1 and talking about increasing and decreasing functions and relative extrema. Briefly, the goals of chapter 3 are going to be using all of the derivative tools that we've developed in application. And I don't just mean in word problems, but applying the derivative for basically all the terminology you see here, using the derivative to look at increasing and decreasing, look at the concavity, that is the curvature of some function, and exploring some applications in economics and maximizing and minimizing things. So first video, we're going to talk about increasing and decreasing functions. So some definitions that don't actually involve any calculus at all or derivative stuff to begin with. So the definition of increasing is that whenever you move rightward on a graph and you get points that are heights on the right side that are greater than the heights on the left side, the graph is increasing, the function's increasing. So we could pick any kind of input, and the only reason we say a less than b is so that we're making sure that we're moving this way on the graph. So if we do that though, and we move to the right, the graph is always headed upward. So at least on that interval from a to b, this function's increasing, although it looks like from what I've drawn that it would be increasing over all those numbers. Okay, and then similarly decreasing, we're still moving to the right, so we still want to have rightward motion, but instead we've got a graph that's falling. So if we pick some inputs, a and b, and the output on the right side is lower, that is f of b is smaller than f of a, then we've got a decreasing function. Okay, so this is us falling from there to there consistently. So if we take a familiar picture, a parabola, we could actually come up with a formula for this without too much trouble, but let's just imagine we're working on the interval from 2 to 8. And so what we can see basically is that this graph is sloping all the way downward until it gets to somewhere around here, it kind of bottoms out, and then it works its way upward again. So we could say that it's decreasing from -2 to 3. We could probably expand this leftward, but as far as the graph is concerned, it stops at -2. So that's as far as our interval is going to look as well. So from -2 up until an x value of 3, this function is headed downward, so we say it's decreasing. And then from 3 on out, from 3 to 8, the function's increasing. There's something that often gets messed up when we do these. These are x values that we're considering. So these are intervals of input. The y values actually don't get talked about at all, really. We're being told they're either decreasing or increasing. That's where the y values kick in. But all these numbers here are x values. These are intervals of inputs. So we'll try to keep that in mind. Okay, so connecting this definition with the derivative stuff we've been working on actually isn't all that far-fetched because we've already been using this kind of interpretation when we talk about derivatives. So if we have a positive derivative, that means the slopes are positive, and that implies that this function's increasing on that interval. So this probably isn't news to you, but we're just formalizing it here. Similarly, if the derivative is negative, then our function is decreasing. I'm going to fix that while we're here. You can watch the process. Obviously, this should be decreasing because we have a negative derivative. Don't want to let that one slide. Great. Negative derivative means decreasing function. Okay, so let's see if we can put this to work. So here's our list price for paperback at a bookstore. And this is a typical kind of demand function, except that we're looking at x as the quantity sold. So this output here is actually a price. So dollars per book when we want to sell X paperbacks. So there's the other side of this. The bookstore buys these paperbacks, maybe from the community or a wholesaler or something, but they get them on the cheap for $1 each. And then the bookstore just has a fixed daily cost of 50 bucks. It's our job to find the daily profit function and then figure out where it's increasing and decreasing. Okay, so first it makes sense to get a profit function before we can do anything with it. As usual, this profit function is revenue minus cost. Revenue minus cost, the difference of these two things. So maybe let's get a revenue function first. And also pretty typical, we have quantity times unit price as our way of establishing revenue. So x is our variable, but we'll go back and snag p of x to include that actual formula. Now this certainly looks like a function of x, but we could also expand it a little bit and get a nice concise expression without any parentheses involved. So then if we want to get cost, then this is, I don't know, I don't want to claim that this is always the way to go, but cost often does have these two components to it. Sometimes one of them is way more complicated and this isn't super helpful, but there's usually a cost associated with the actual production of the items. Sometimes that's just a number times x. Sometimes it's more exciting, and then there's usually some kind of fixed cost, some kind of overhead that they have to pay no matter what no matter how many items they produce. So this might be leasing a facility or buying machinery or paying for supervisors or labor, that sort of thing. Okay, but since they buy the books at $1 each, that's 1 times x for our variable cost. So variable cost is 1 times x, and then we were told they have a daily overhead of $50. So that's because it doesn't rely on how many books they sell at all. They have to be open. Then there's a fixed cost. So no x is attached to that. Okay, so put profit together, we get revenue minus costs. There's a little bit of like term combination that happens here. We've got 10x, and then we're taking away x, so we got to get 9x. But everything else just kind of stays the way it is. I guess one thing to be careful of is this is minus 50 since it was in these parentheses here. Okay, so we've got our profit function, and now it's time to think about increasing, decreasing. That was the second, the follow-up question they asked us. So the graph of profit looks something like this. And we can kind of get an idea of what's going on. I think there are a couple of different reasons why the graph wouldn't exist on the left side here, but a pretty good reason that we can think of is that would involve the square root of a negative, which isn't a real number. But also keep in mind this is x is quantity of books sold, so it probably doesn't make sense to have negative values of x anyway. So just eyeballing this, it sort of looks like right about there, some number before 40. I'm not totally sure what that is, but it's definitely above 30, maybe 35-ish, a little bit bigger. So it looks like profit is increasing until we sell however many books that corresponds to, 30-something. And then it's decreasing from that point forward. But actually, we can do this exactly if we rely on some calculus, basically, the algebra, as it were. So one thing we were just told is that if the derivative is positive on some interval, then we know that function is increasing. And if the derivative is negative, the function is decreasing. So if we can figure out where the derivative of profit is than 0 less than 0, then we can make some claims about increasing and decreasing. Well, first we need a derivative function. So p prime looks like the derivative of this thing. And let's see, so just power rule all the way through. Derivative of 9x is 9. The 3/2 power comes down, and we're down to a 1/2 exponent. And then derivative of a constant is just going to disappear. So let's think about increasing first, and we'll go for setting this derivative greater than 0. That's what if this were greater than 0, then our function is increasing. Okay, so we got a little algebra. Ooh, let's not go too fast. So if we take away 9 from both sides, that's nothing groundbreaking there. And then here's where something kind of interesting happens. You might note that from 1 to the next line, the direction of our inequality has changed. It was a greater than, now it's a less than. And if you remember, that's because the next step here would be to get rid of this negative 3/2. We would do that by multiplying both sides by negative 2/3, say. Inequality always changes direction when we multiply or divide by a negative number. So this flips around. Negative, negative makes positives for each of these things. We could tidy that up a little bit. And then to get rid of the 1/2 power, this is just like a square root, so we could square both sides. But let's see, this looks like 18/3, which is just 6. 6 squared is certainly 36. Okay, so profit function's increasing on the interval 0 to 36. There is a little subtlety here that we're kind of ignoring. Usually when we would square this, it gets a little more complicated, but we don't have to worry about the negative side of these values. So actually, it's safe in this instance to only pay attention to x, what x is less than. Anyway, so this shouldn't be a big mystery, because if we've got on one side the function's increasing, then probably the other side the function's decreasing. But just to reinforce that, we take a look at the same derivative thing. This is just p prime of x back again. And we're making sure that if we set it less than 0, that what we get is all the other intervals, basically. But it's going to be the exact same solving process. We're going to subtract 9. We're going to multiply by negative 2/3, so it's going to change the direction of the inequality. And then when we square, we're going to get 36. So the exact same number on the right side as we got for increasing, but now it's greater than. Since we don't have an upper bound, we just keep going from 36 onward. So the profit is decreasing from any values greater than 36. So one note about this, and I'll go back to the graph just to illustrate. So this should reinforce what we came up with from our picture. The number below 40 that we were thinking about turns out to be 36 exactly. And calculus is what helped us figure that out, which is nice. And if you notice that this covers all the territory. From 0 to 36 it's increasing, and then from 36 onward it's decreasing. One interesting question is it increasing or decreasing at 36? And the answer in this case is that it's neither increasing nor decreasing. It's like throwing a ball up in the air. There's that split second when it reaches its peak, its apex, when it's not moving up or down for just that infinitesimally tiny instant. So that's going to be a really important instant for us moving forward. But that's it for increasing and decreasing. We'll be back to talk about relative extrema.